This is the pre-class lecture for Friday, November 9th. So we're going to start chapter 7 today with some basics on alkenes. We're going to look at the sort of review the structure and our syntheses, and then talk a little bit about naming alkenes and go into cis-trans naming as well as what's called EZ naming. And then sort of expand a little bit upon our stability of alkenes that we talked about in Zaitsev's rule. So looking at the beginning of chapter 7, we're looking at this functional group. We're now going to talk about an alkene, which is our carbon-carbon double bond. And so for an alkene, what we know from the beginning of the year is that the carbons in a carbon-carbon double bond are sp2 hybridized. They have an unpaired or an unhybridized p orbital, and that one electron in each one of those unhybridized p orbitals overlaps then to give us the pi bond, and then in between the two carbons is a sigma bond. And so we've talked about that. We talked about that when we first started talking about hybridization. And the key thing with the carbon-carbon double bond is that it forms geometric isomers that are not that are not interconvertible, because in order for us to, let's say we started with maybe a chlorine here and a chlorine on this side, there is no way to convert that molecule to this molecule without breaking the pi bond, which would then allow us to rotate. If we broke that pi bond, we might be able to rotate around the carbon-carbon single bond and be able to convert, let's say, the cis isomer into the trans isomer. But this requires an incredible amount of energy to break the pi bond, and so this does not happen at room temperature. It might happen at higher temperatures, but it certainly is not going to happen at room temperature. So these are geometric or stereoisomers, and these specifically would be called cis-trans isomers. And I'll come back to that in a minute in terms of how we formally name cis-trans isomers, and then also related to that is the EZ terminology. And that's E, letter Z, not EASY. So in terms of the double bond, we've talked about that. Now, the double bond is the first molecule where we have what's called unsaturation. Now, alkanes are considered to be saturated hydrocarbons. That's what an alkane is. And what that terminology means is that if you have a saturated hydrocarbon, it means that you have the maximum number of hydrogens possible per carbon. And we're only talking about hydrocarbons, so we're only talking about carbon and hydrogen in the molecule. So for an alkane, the general formula is CnH2n plus 2. So that would give you the maximum number of hydrogens per carbon atom. And so, if you have one carbon atom, the most hydrogens you can attach is 4. And that fits that formula of CnH2n plus 2. Now, when you get to double bonds, what happens is that you lose 2 possible hydrogens for every double bond that you have. And so these are called unsaturated. And it's not just the carbon-carbon double bond, it's what we'll see later on that happens with the carbon-carbon triple bond. So unsaturated hydrocarbons are alkenes, and later on the triple bond, which we'll call alkynes. So for a double bond, if we come back up here and let's replace this this 2-carbon molecule with the maximum number of hydrogens, what you can see is that this formula is C2H4, which means that the generic structure for an alkene is CnH2n. So what we've done is we've lost 2 hydrogens from the maximum number of hydrogens that you can have per carbon. And so that's why it's called it unsaturated. Now, if you've heard saturated and unsaturated in, let's say, popular culture, in particular in food and nutrition, the reason for that is because there are saturated and unsaturated fats. And basically a fat molecule is to have a carboxylic acid attached to, let's say, if you have a triglyceride, it would look like this, where you have a 3 OH groups attached to 3 carbons. That's the molecule called glycerol. And then you have 3 basically esters, and those esters have long carbon chains. And so these long carbon chains can either be alkanes, and if they are, then that gives you the term that they are saturated fats. Or this long chain can somewhere have a double bond in it, or maybe more than one double bond, and at that point they're called unsaturated fats. So that term that's used in nutrition comes from the fat either having the long chain as an alkane or as an alkene. And of course, if you have more than one double bond in your chain, then you have a polyunsaturated fat. And also, depending on whether this double bond is cis or trans, we can have trans fatty acids or trans fats, which I believe are the bad ones for you. So if there are double bonds in your triglyceride, which is just another word for a fat or an oil, then you have these terms of saturated and unsaturated and polyunsaturated. So that's where you hear about that terminology in the popular literature, nutrition, on TV, etc. Now going back to this formula, so for alkanes you have a general formula of CnH2n plus 2. For alkenes it's CnH2n. What happens is that formula of CnH2n is not only just for the double bond, but it's also for rings. So a CnH2n also holds for cyclohexane because that's C6H12. So in general, we have these things called degrees of unsaturation. And you'll use this next semester in the laboratory course when you start talking about how to use different techniques to determine structures of molecules. One of the simplest things that you can do is to have the molecular formula and use what are called the degrees of unsaturation, or what your book calls the elements. These are also called the elements of unsaturation. And so a degree of unsaturation basically means that you have one ring or one pi bond. And the way we calculate those is using a formula that says the degrees of unsaturation equal, let's see, minus, you have a slightly different formula in your textbook, minus 1/2 times 2 times the number of carbons plus 2 minus the number of hydrogens. Okay. And so that's actually a formula that we can use to calculate how many degrees of unsaturation that you have in your molecule. So let's see if this actually works. And I don't know why there's a minus 1/2. That doesn't make any sense, but let's see how it does. So let's calculate the degrees of unsaturation for cyclohexane. So we'd have 2 times the number of carbons, which is 6, plus 2, minus the number of hydrogens, which in this case is going to be 12. So this formula from the textbook is totally messed up. Sorry, I should have. It's actually 2 times the number of carbons minus the number of hydrogens over 2 minus 1. That's the actual correct formula with one small problem. It's the number of carbons minus the number of hydrogens over 2 minus 1. So it's actually, I think, plus 1. So if we come back to the C6H12, we have 6 carbons minus the number, that's going to be a plus actually, over 12 over 2 plus 1, so 6 minus 6 plus 1 gives us 1 degree of unsaturation. So this is the actual correct formula for the number of degrees of unsaturation. And I still don't quite understand why the book has it written the way that it is, but it is what it is. So this is the formula we use. So if I said I had a molecule that was C8H, let's say 16, and you wanted to know how many rings or pi bonds are in this molecule, you would say, okay, I've got 8 minus 16 over 2 plus 1, so that will give me 1 degree of unsaturation. And that means this molecule could either have 1 double bond or 1 ring. If we have benzene, and benzene looks like this, it's got 6 carbons and 6 hydrogens. If you calculate the degrees of unsaturation for benzene, you get 6 minus 6 over 2 plus 1, which is going to be then 6 minus 3 plus 1, which is 4. If you come back to benzene, benzene has a ring and 3 double bonds, so it does indeed have 4 degrees of unsaturation. And when you look at problems next semester in lab, if you find that you have 4 degrees of unsaturation, what that means 9 times out of 10 is that you have a benzene ring in your molecule. So if you use this correct formula, or at least what I think is the more correct formula, then what you end up with is you end up calculating the degrees of unsaturation. That tells you how many double bonds or rings are in the molecule. Okay, so sorry for not understanding why they put that formula in the textbook, but it is what it is. Okay, so the next thing that we need to talk about is how do you name alkenes? And the rules for naming alkenes are going to be very similar for the rules of naming alkanes, except that we have to take into account the double bond. So the first rule is you're going to find the longest continuous carbon chain, with the carbon-carbon double bond in it. Okay, that's one difference between the alkenes and alkanes. Then, once you find the longest continuous carbon chain, then you're going to number from the end closest to the carbon-carbon double bond. So the carbon-carbon double bond is going to set the precedence for the naming And so it's not the end closest to the first substituent, it's the end closest to the double bond. If the double bond's equal from both ends, then you break it with the tiebreaker of looking at the substituents. And then you're going to name and number the substituents as you did before. And so your name is going to have your alphabetized list of substituents, followed by a dash, followed by a number, followed by the parent name, or actually the prefix, followed by ENE. So the prefix here gives the number of carbons. So that's your meth, eth, prop, bute, pent, etc. Your alphabetized list of substituents then is as we did before. So here are some alkenes that we've made when we were talking about doing E1 or E2 eliminations. For one problem, we made this alkene and we made this alkene as the two possible products of an E2 elimination. How would we name them? Well, in this case, we have a 4-carbon chain, so this is going to be a butene. So the ene suffix tells you that there's an alkene, that there's a double bond in the molecule. Now, we number from the end closest to the double bond, which goes 1, 2, 3, and 4. What's this number that's in front of the parent name or the prefix? Well, that number is the first carbon in the carbon-carbon double bond. So this would actually be called 1-butene. So that means we have a 4-carbon chain with a double bond in it. Where's the double bond located? It's located between carbons 1 and 2. That's how we interpret it. So what would this molecule be called? This would be 2-butene. And so again, it's a 4-carbon chain with a double bond located between carbons 2 and 3. So it's the first carbon, the number of the first carbon in the carbon-carbon double bond. Let's get a little more tricky here. So what would be the name of this molecule? If you really want to test yourself, turn off the video and try and name it and then come back and see if you got the name right. Longest continuous carbon chain in the molecule is this one. The longest continuous carbon chain, it contains the double bond. Which end do we number from? Left to right or right to left? Well, if we number from left to right, we go 1, 2, 3. We encounter the carbon at 3. If we go from right to left, we go 1, 2, 3, and we encounter the double bond at carbon 3 as well. So we have a tie, so now I'm going to number from the end closest to the first substituent, and so that's going to be this. So I've got 1, 2, 3, 4, 5, and 6. And if we had ties at that point with numbers of substituents, we'd break them like we did before. We would use the double bond, we would use the alphabetization, etc., to break that tie. Okay, so what am I going to call this molecule? This molecule is going to be called 1-chloro. It has a 4-methyl. Then where is the double bond located? Between carbons 3 and 4. 3-hexene. So this is 1-chloro-4-methyl 3-hexene. Okay, let's try one more. Okay, I'm going to locate the longest continuous carbon chain that has the most number of carbons in it, and I'm going to choose this one. And you might say, why would you choose that one and not the other one? Well, because that's going to give me the longest continuous carbon chain with the double bond and with the most number of substituents, like we did before. Now, am I going to number this from left to right or right to left? I'm going to number it from right to left because going in from left to right, I go 1, 2, 3, and I encounter the double bond from right to left. It's 1, 2, 3, and so there's a tie. So now we go with the first, the end closest to the first substituent, which is going to be the right end. So 1, and then then the chlorines at carbon 2, 3, 4, 5, and 6. So now we would have our name, which would be 2-chloro, 3-ethyl, 4-methyl, 3-hexene would be the name of that molecule. Okay. Now, actually, that's not the real name of the molecule, and I'll come back to it in a minute. Well, I'll come back to it in a couple minutes and tell you what the real name of this is, because I'm missing something from this molecule. How do you do cycloalkenes? For instance, what would the name of this molecule be? Well, when you're naming cycloalkenes, we always assume that we number so that the double bond gets carbons 1 and 2. Now, in this particular case, I'm going to number carbon 1 and carbon 2 so that I have actually two ways. I could go top 1, bottom 2, or bottom 1, top 2. But in this case, my tie then, I'm going to number the top carbon number 1 because it's got a substituent attached to it. So this is a little different than cycloalkanes because I'm going to have to number so that the carbon-carbon double bond gets carbons 1 and 2. That's absolutely has to happen. Okay, so this would be 1-methyl cyclohexene. Now you may say, do you put the number of the double bond in before the cyclohexene? You don't have to because it's understood that the number 1 and number 2 carbons, that's where the double bond is. So you don't have to say 1-methyl 1-cyclohexene because it's assumed that the double bond is between carbons 1 and 2. How about this molecule? What would you call this one? Well, I could number this carbon 1, this carbon 2, and then go around the ring 3 and 4. Or I could number 1, 2, 3, 4, 5, and 6. Well, if there's a tie in terms of numbering carbons 1 and 2, you're going to break that tie by then numbering it so that you not get the lowest total sum of substituent numbers, but actually number it so that after the double bond you find the first and closest substituent. So in this case, we would get rid of this numbering scheme up here, and we would number it 1, 2, 3, 4 that way. And so this would be 3-chloro, 4-methyl cyclohexene, because again, it's assumed that the carbon-carbon double bond is between carbons 1 and carbon 2. Okay. think you can have multiple double bonds in a molecule? If you do, let's say I've got this molecule. When you have double bonds, when you have more than one double bond in the molecule, then you're still going to number from the end closest, I believe, to the first encountered double bond. So this would actually be numbered 1, 2, 3, 4, 5, and 6. So there's my longest continuous carbon chain. With a methyl group at 3, this would be called 3-methyl. And now I'm going to put in the numbers, the beginning numbers of each of the double bonds. So this would be 1, 4, and then this is a 6-carbon chain, so hex. And then what I do is add the letter A, and I say diene. So this is 3-methyl 1,4-hexadiene. So what that means is I've got a 6-carbon chain with 2 double bonds in it. One double bond starting at carbon 1 and the other one starting at carbon 4. And then I've got a methyl group on carbon 3. So we can have lots of dienes or trienes. This molecule that's this particular diene is used to make the rubber that goes into either automotive tires or airline tires. This is actually called 1,4-butadiene. Or sorry, 1,4-butadiene. 1,4-butadiene. No, 1,3-butadiene. It's 1,3-butadiene. So 4-carbon chain, 2 double bonds starting at carbon 1 and 3. And so you can have cyclic molecules that have 2 double bonds. This would be 1, 3 cyclohexadiene. And so on. So you can go through the remaining of the IUPAC naming, in your textbook, but these are the basic rules that we use. They're very similar to what we have for alkanes. Now I do want to talk a little bit about how you name the geometric isomers or the stereoisomers of carbon-carbon double bonds. So when you have a carbon-carbon double bond and you have a hydrogen and a non-carbon group or non-hydrogen group attached to one carbon and another hydrogen and non-carbon or non-hydrogen group attached to the other carbon, then you can use the terminology cis and trans to name the stereochemistry of the double bond. So for instance, in this case, either the 2 hydrogens or the 2 chlorines are on the same side of the double bond. So I would call this molecule, I'd actually call this cis 1,2 dichloroethene would be its name. Okay. What would the name of this molecule be? This would be trans 2-butene, because there's my longest continuous carbon chain. And so I have either the hydrogens are trans or the non-hydrogen groups are trans. So cis and trans can only be used when you have a hydrogen group and a non-hydrogen group attached to each of the carbons in the double bond. Because in that case, it doesn't matter whether you look at the two non-hydrogen groups or whether you look at the two hydrogen groups. You will determine then whether it's cis or trans by looking at those two, at the two groups. So you can even mix them. You could have something like this. And so this would actually be, wait, whoa. That one I'm coming to. This would be cis 1-chloro propene, because there's a 1, 2, 3 carbon chain. So that would be called cis 1-chloropropene. Okay. Now, what happens if you had two of the same groups attached to either one of those two carbons? Well, the idea of these geometric or stereoisomers is that cis 1,2-dichloroethylene is a different structure, a different three-dimensional structure than trans 1,2-dichloroethene. Right? These are two different three-dimensional structures, but they are of the same structural isomer because these two molecules have a carbon with a chlorine and hydrogen double bonded to another carbon attached to a chlorine and hydrogen. So these two molecules right here are the same structural isomer, but they have different three-dimensional structures. So therefore they're stereoisomers, and in this case specifically cis-trans isomers. Well, molecules aren't cis or trans if they have, for instance, the same two groups attached to one of the two carbons. So if I have two hydrogens here, this molecule is not cis or trans. Why not? Because there's no possibility of two stereoisomers. With both these groups the same, it doesn't matter where the methyl group is, because the methyl group's on the same side as this hydrogen or opposite side of that hydrogen. So that's not cis or trans. And this molecule right here is not cis or trans. Right? Because there's one, a methyl group is on the same side as this methyl group, and a methyl group is on the same side as the ethyl group. So if I switch these two methyl group positions, I do not get a new structure, a new stereoisomer. So when the same groups are attached to one of the two carbons in a double bond, these cannot be cis or trans. Which leads me to the last type of stereoisomer that we can have, and that is, what if I had this molecule? How would I name it? Well, whenever you have three non-hydrogen groups, when you have three non-hydrogen groups attached to the carbon-carbon double bond, you can't use cis or trans anymore. Because if I had this molecule, you might be tempted to say, oh, well, the two methyl groups are trans, which you're allowed to say. You're allowed to say that these two methyl groups are trans, but in the name, if I called this trans, What am I talking about? Am I talking about the two methyl groups? Am I talking about the methyl or the ethyl? Or am I talking about the chloro or the methyl or the chloro or the ethyl? So when you have more than 3 non-hydrogen groups attached to a carbon-carbon double bond, you're not allowed to use cis or trans in the name because it will lead to an ambiguity in the name. And remember, IUPAC names are supposed to give one and only one name for the molecule that everybody will get. So when we have 3 non-hydrogen groups attached to a double bond, we have to use the EZ method. And it sort of is. So what's the EZ method? Well, in the EZ method, what we do is we compare, and I'm going to just write that molecule again. Well, actually, yeah, I'm going to write that same molecule again. And so in the EZ method, here's what I'm going to do. I'm going to compare these two groups that are attached to one carbon, and I'm going to determine which group has the higher priority. And then over here, I'm going to determine which group has the higher priority. And then what's going to happen is I can end up with two possibilities. I can end up with the two high priority groups on the same side, which I'm going to call the Z isomer, or I could end up with the two high priority groups on opposite sides, quote unquote trans, if you will, even though I'm not allowed to use the word trans. And this is going to give me what I call the E isomer. So we're going to compare these two groups and determine which one is the high priority and the low priority. We're going to look at these two groups that are on the other side attached to the other carbon, determine high and low priority, and then I will either call this the Z or the E. Now these are for German rules or words. The Z, when the two groups are on the same side, are called Zusammen. Close enough. Zusammen, I think Zusammen. Yeah, that's Zusammen is the German word, and if I spelled it wrong, then whatever, send me an email or just don't bother telling me. I know I probably spelled it wrong, but this is called Zusammen, which in German is translated as being together. That's my one semester of German my senior year taught me, because I went to a state school where we didn't need to have a year of foreign language. And since I thought I was going to go into organic when I went to graduate school, a lot of the primary literature was written into German. So I took my one semester to prepare me for graduate school, and when I got there, that requirement of having a reading knowledge of German was no longer in. So pretty much I remember Zusammen, and I remember E, which stands for Enthagen, which I believe is a cross. So these are the equivalent of cis and trans, but they're not the equivalent of cis and trans because we're using them when we have 3 or more non-hydrogen groups attached to a double bond. So you might say, okay, how do you determine the high and the low priority then? Well, we're going to determine high and low priorities using our friends, the con-angled sequence rules. And if you're sitting there going, what are those? Those are what we use to determine the priority group 1, 2, 3, and 4 in RNS. Those were called the con-angled. Actually, it's the con-angled pre-log sequence rules. So we just use those rules, which we hopefully haven't forgotten, to compare chlorine and methyl. So which one wins? Chlorine. Methyl versus ethyl, which one wins? Ethyl. What is this molecule then? That molecule is the entogen or E isomer. So when I write the name of this molecule out, since it has a 5-carbon chain here, I would name this E 2-chloro 3-methyl 2-pentene. Okay. So I can actually write lots of double bonds and ask you if they're the E or the Z isomers. And really all I'm doing is just saying, can you determine the con-angled pre-log sequence rules for these two guys? And can you apply those then to these two? Which hopefully you still can after RNS. And if you can't, well, remember the final's not that far in the distant future, so you got to keep these things in your mind. So if I did this, chlorine versus oxygen, chlorine wins. Carbon versus carbon, this carbon right here has a carbon, a hydrogen, and a chlorine, versus this carbon having 2 hydrogens and a carbon. That one wins, and so this is the Z isomer. Okay, it's as easy as that. E and Z. It's been a long day. Okay, so that's how we determine the naming for molecules that have 3 or more non-hydrogen groups. Now, back here, I had a molecule like that. It was this one. So this molecule we had named 2-chloro-3-ethyl-4-methyl-3-hexene. Is this E or Z? So I'm comparing ethyl and methyl. Ethyl wins. Ethyl and a CHCl, CH3, and so this group wins. So the actual correct name of this molecule would have been E 2-chloro-3-ethyl-4-methyl-3-hexene. Okay, so we either, when we get geometric isomers or when we get stereoisomers, we either use the EZ or we use the cis or trans. Now, we don't have to worry about that for rings. You can read in your textbook. Basically, you need like an 8-membered ring to have a trans orientation of the double bond, so we don't worry about the rings. But this trans 2-butene, since hydrogen always has the lowest priority, you could very easily call this E 2-butene. So E can always be used, but cis or trans can only be used if you've got 1 hydrogen and 1 non-hydrogen group attached to each of the 2 carbons in the carbon-carbon double bond. Okay, so the E molecule is, E can always be used, but cis or trans only for special molecules. Okay, so that's how we name the different stereoisomers of a carbon-carbon double bond. Okay, and then the last thing that we want to talk about is in this initial discussion or initial setup of alkenes is the stability of alkenes. Now we touched upon this. We didn't touch upon it. We talked about it. In terms of the stabilities of alkenes, that's going to depend on the substitution or the number of substituents. And by number of substituents, I mean alkyl substituents. And we know that the number of alkyl substituents gives us the stability, and basically the more alkyl substituents around the double bond, the more stable that double bond is. That was we used in conjunction with Zaitsev's rule. And in a carbon-carbon double bond, you can have a maximum of 4 alkyl groups attached to a double bond. What we said was that a double bond is an electron withdrawing group. It loves to have electron density pushed towards it. The more electron density you push towards the carbon-carbon double bond, the more stable it is. So when you attach an alkyl group to the double bond, the hydrogens become delta plus because they have some of their electron density sucked away from them by the carbon. That carbon then has its slight negative charge that it can push towards the carbon-carbon double bond, and the more alkyl groups, the more pushing of electron density, the more stable the double bond. But how do we actually even know that a double bond with 4 alkyl groups is more stable than one with 3, than one with 2, than one with 1? Well, I'll introduce this here as the last topic, and it's in your textbook, but what we do is we use calorimetry. We measure heats of reaction in order to determine stabilities of molecules. And here's how we do it for alkenes. If you take an alkene and you treat it with hydrogen gas and a catalyst like palladium or platinum metal, and we'll get into this reaction in a few days or weeks, you actually add the two hydrogens across the double bond to make an alkane. This is actually what's called reduction. In the yeast lab, I introduced the idea that in organic chemistry we talk about oxidation and reduction by looking at the atoms that are added or removed from a molecule, because it's a little difficult to keep track of the electrons that are actually moving like we do in general chemistry, where we have, in general chemistry, we have lose electrons, oxidation, and gains electrons, reduction. That's my favorite because that's Leo the lion goes grr, but I digress. In organic chemistry, when you add hydrogens, that's reduction. When you gain oxygens, that's oxidation. And it's either add hydrogens or lose oxygens will give you reduction, and gain oxygen or lose hydrogen will give you oxidation. So a typical reduction reaction is to take a double bond, add 2 hydrogens across the double bond, and form the carbon-carbon single bond. So alkenes can be reduced to alkanes. And this turns out to be an exothermic process. And so here's what we do. Let's say I wanted to know whether 2-butene, and I've got myself in trouble here. But I'll get myself out. let's say that I wanted to compare one butene to trans 2-butene to cis 2-butene. And I wanted to determine which one of those was the most stable and which one of those was the least stable. Well, what would you predict? Well, you'd predict that the 2-butenes, that these two, the left and the center, are more stable than the 1-butene because the 1-butene has just one alkyl group substituent and the 2-butenes have two alkyl groups. Now, could you guess as to which one's more stable, trans or cis 2-butene? And so if you guess that the trans 2-butene, where the methyl groups are far away from each other, that would be the most stable. You're correct. That having the two methyl groups on the same side of the double bond would be number 2 stability. And then the 1-butene would be least stable. And that's exactly how stability would work, but how do people determine that? Well, here's what they do. They take each and every one of these molecules and they add H2 with the palladium catalyst to each one of these molecules. Now, if I do that, what product do I make in each case? If you said that in each case I make the same product, butane, you are correct. So the key about doing calorimetry to determine whether one molecule is more or less stable than the other is that you have to form the same product in the reaction. So if I come over to my next slide here, and I get rid of my 2 that carried over somehow. Let's say I take the cis 2-butene and I react it with hydrogen gas. So I'm going to take hydrogen gas plus this. So what product am I going to make? Well, I'm going to make butane. And so if I put this on an energy coordinate diagram, this energy difference is going to be what we call the delta H of, and I might as well use this term, this is called the delta H of hydrogenation, because adding hydrogen across the double bonds is called a hydrogenated, it's called a hydrogenation reaction. Little aside here, where have you heard hydrogenated in nutrition? Well, you have partially hydrogenated double bonds, and that comes about when you try and take a liquid oil, because usually, remember the fats I talked about, I don't know, 20 minutes or an hour ago, and you have a double bond in that long chain of the fat. Well, when you have double bonds, typically that fat becomes an oil, which just means it becomes a liquid at room temperature. And if you want to make a solid fat out of it, you have to hydrogenate it and turn it into a saturated alkane, because the saturated alkane fatty acids tend to be fats or solids. So if you want to make Crisco, you take a vegetable oil and you hydrogenate it to make a solid. And if you only partially hydrogenate it, then you make a partially hydrogenated fat, which is, evil because it will kill you, or it will, I don't know, it's bad nutritionally. So the key thing is I get a delta H of hydrogenation, and since this is exothermic, I'm giving off energy to go down to the alkane. Now in each one of these reactions, I'm going to be producing the same product. So that gives me kind of an anchor point for my energy plot, because every one of these products, or every one of these reactions, goes to the same product. So now if I found out that this was, I'll just make up a number, minus 50. Now I do my trans And let's say I found out that my trans hydrogenation, my heat of hydrogenation, was only like minus 40. Well, what does that mean? Well, if they all went to the same products, I go up 50 energy units, and here I only go up 40 energy units. So here's the energy level of cis 2-butene. Here's the energy level of trans 2-butene. Which one's more stable? The one with the lower energy. And so I can get that energy if I go to the same product every time, and I know what the heat of hydrogenation is, which I can measure using some sort of calorimetry technique. And what about the 1-butene? Well, the 1-butene would be way up here because it's going to produce more energy when it gets hydrogenated because it's less stable. So maybe it gives like minus 65. So the least stable molecule gives off the most energy. The most stable molecule gives off the least amount of energy. And so this is how we actually measure, or how we prove that one molecule is more stable than another, is that we choose molecules and reactions so that we get the same product each time, so that way, if the reaction's exothermic as this one is, the one with the biggest negative heat of hydrogenation is the most unstable alkene. And the one with the smallest heat of hydrogenation, exothermic heat of hydrogenation, is the most stable molecule. So this is actually how we determine whether a molecule is more or less stable than another one, is using this calorimetry technique. But the key is that you have to form the same product each time. Okay. So that sets up the basics then for alkenes. And now what we need to talk about on Monday is how do we make alkenes? Well, we already know E1 and E2, but I'm going to throw a couple of more in here and talk about how we take and make OH group sleeve, which will involve the addition of acid to make the OH group a viable leaving group. Okay, so I will put an online quiz so that you can take that. And so on Friday, we will talk about naming and easy cis-trans. And if you have any questions about this calorimetry, we can go back over that as well.